Okay, so now let's go to another level of complexity by talking about the code that runs this whole thing. I chose compile code over Python, which is an interpreted language, because I wanted to avoid any possible timing issues. I wanted this executable to be able to run as fast as possible. The pigpio library was chosen since it is capable of measuring periods down to around 10 microseconds with reasonable accuracy, even though the operating system, which is Linux, is not a real-time operating system. Seems that this library works pretty good using its methods. The opencv library runs the video capture and processes the image operations. Now the CSI camera is used by opencv through the loadable kernel module that is provided, but you need to either manually load it each time, or in my case I change the boot up file so that it is automatically loaded at boot time. The pygpio example code freakcount2.c is used as the framework for the main thread. All video operations are done in a separate thread. Main thread and video thread use a mutex when global data is addressed by either. Let's now look at the code. As stated earlier, the program uses the pygpio example freakcount2.c and then builds on that file. I chose to put everything in a single file rather than separate out some functionality into a separate file. This made it easier for me to develop this code using simply a text editor. Note that I chose to write this in C++ so as to use the features found therein. Note also the whole list of includes that are now needed. Then there is the somewhat complete description, how to start the program with its required options. Let's skip down to where a struct is defined that contains the needed data that the main thread needs to send to the video. Also note that here we define the mutex needed to prevent collision between the two threads. Since this program will loop indefinitely, we need a mechanism to exit gracefully. Linux libraries do not contain any version of kbhit that is found in Windows. So here are a set of functions provided by someone on the web that provides this functionality. Hitting any key will cause the program to exit. Recall that one might implement turning the gun oscillator on and off programmatically. Here are the functions that perform those operations. Next, we encounter the video thread. Let's skip over this and come back to it at the end. We then find some functions provided in the original pygpio example. The more significant one is the void samples function. This is the callback function that the underlying pigpio daemon calls every millisecond when there are level changes. When a main thread sets gset counts to 1, the pulse counter resets to 0 and the counter begins to count for another period of time set by the -R option before another reset will occur. Now let's step through some of the more significant steps in a main thread. The first part consists of a series of initializations. Then there's the definition of target. Recall that incoming pulses begin to arrive only when a car passes in a radar beam. So target is a threshold level of pulse counts that is used to begin a program loop, making speed measurements and communicating information to the video thread. This shall be seen in a moment. This line begins the daemon clock. Then we skip over some functionality that is not used and arrive at the main program loop. The loop time is the numeric value passed by the -R option times 0.1 second. A value of 1 or 2 works well. This means that while the car is in the beam, a speed measurement is being made every 0.1 or 0.2 seconds. Typically, a passing car remains in the beam for a second or more. Now, as mentioned, when a car enters the beam, the value count 0 will exceed the value target. And this if statement takes over and a cycle counter is begun. The logic found here does two things. It finds the maximum speed out of the series of measured speeds and sends to the video thread a flag telling the thread to stop capturing images and hold or retain the current image until further instructed. In the code shown, this flag is sent on a third measurement cycle. In this case, it was experimentally determined for the particular setup when the car was approximately centered in the field of view of the camera. When the pulse drop counts to nearly 0, this if statement no longer applies. But before leaving it, it sends to the video thread the maximum speed value and a flag telling the thread to now save the image that is being held. Finally, let's look at the video thread. Opening the camera is straightforward since the Video for Linux 2 driver is loaded. Then, importantly, we save the image as a PNG file since its compression is lossless and we want as much resolution as possible so we can read license plates. Then we have the main program loop. It continually reads frames from the camera and stops reading only when it receives a snap flag from the main thread. The current frame remains in memory until a save flag is received. At this point, the current frame is rotated 180 degrees since the mounting of the camera is upside down. And then the maximum speed value is added to the upper left-hand corner of the image. Finally, a file name is created out of the timestamp, and speed value, and the image is then saved in the current directory. That's it.